start so we don't penalize people for a long time here. And we'd like to welcome Csaba and Wojciech Reguła, and they will talk about ways to bypass macOS privacy mechanism. Give them more.
Thank you. So yeah, we will talk about how to bypass privacy on macOS mostly, or partially also thanks to iOS. My name is Csaba Fitzl. I'm working at Offensive Security as a content developer. I'm the author of the macOS Control Bypasses training. I developed the Shield app for macOS, which is like an exploit protection application for macOS. It's free, open source, you can download it. I used to be a Red Hat blue teamer in the past. I have 2 kids, wife, and I like to do hiking in my free time. And actually I will go to Pakistan in the next couple of days.
Yeah. So, it's my member. My name is Wojciech Reguła. I'm a principal IT security consultant at Securing, and in my day job I mostly focus on iOS and macOS application security. I run a blog with my crazy name that you can see on the slide. Somebody of you may also know me from an open source project, iOS Security Suite, that helps developers to make sure that the iOS application is run on a trusted device. And recently I've started a new service that is macOS environment security testing. So if you have macOS computers in your organization and you want to test them, feel free to reach me out. So yeah, this presentation was a result of joint research. We initially run it on Black Hat in Las Vegas in USA this year. This is the updated version, the second run of the presentation. And according to the question during the last presentation, we will have something positive to say because all these vulnerabilities are already fixed. So yeah, and there are many more vulnerabilities than we included on the presentation, but 45 minutes is not enough to tell you about everything, so we can select the most interesting parts. So the quick introduction, because we don't have many macOS users in the audience. So on macOS, almost every security mechanism starts from the system integrity protection, called the SIP. It's based on Sandbox kernel extension, and because it's system integrity protection, it cares about the system integrity. So it restricts access to many directories on macOS. It will also deny debugger if you try to debug or somehow inject your system processes. It will make sure you cannot do this. And the third important thing in macOS, if you have root, you are not a god. Even if you have root, you cannot modify some system resources, and that's why the system integrity protection is in place. And when the system integrity protection is turned on, it's turned on by default. There's additional layer of security called transparency, consent, and control framework, and the abbreviation is TCC. And if you, for example, your application tries to access some privacy resources, you will see the following prompt. If you use iPhones, you are used to that prompt. For example, if your application wants to use camera, you will have a prompt, hey, this application wants to use the camera. So the very same mechanism is on macOS. On the slide, for example, when you try to access contacts, the contacts database, the TCC will prompt you with another terminal application wants to access your contacts. These resources may be contacts, calendars, reminders, photos, screen recording, microphone, and others. TCC is a bit granular because, for example, in automation, you can grant one application for a permission to control other applications. For example, Microsoft Outlook can control Skype for business, right? And from our security people perspective, SQLite-free database is under the hood. So all the permissions you grant or refuse are stored in an SQLite-free database. That's very important. And there is one global database for a system TCC that will care about global permissions, like for example full disk access. This is a crucial permission. And each user on macOS, because macOS is multi-user system, so you can have more than one user. Each user will have their own TCC database, because for example one user wants to give, I don't know, Skype to access the camera, but the second user on macOS, for example, doesn't want to give the permission to camera access. So yeah, each user has its own TCC SQLite database. And briefly, what's in the TCC database? The first column you have the permission type. So for example, access to camera, KTCC service camera. The client column is about bundle identifiers of the applications. Out value contains the value if the permission is granted or not granted. And then the last one, the code signing requirement, very important from a security perspective. The quotation marks are because it's not printable, but it's binary data containing code signing information. But this code can translate this binary form of the code signing requirement into human readable form, and this code signing requirement says that the main executable that requested the access to the privacy resource was signed with a certificate issued by Apple with all this leaf information, and this is the team identifier of the developer that's requested for the Apple issued certificate. So it was an executable signed with a typical Apple developer certificate. Okay. And now,
so TCC has another leg. So this database is one part of the entire setup, but TCC has also handles user intent. So the previous one was user permissions, like you get a pop-up and you grant access. But let's say you do something like drag and drop, and the system will implicitly recognize that you want to give access, let's say, to a file, to a certain application, and it will handle it transparently. So when the user shows an intention to do something, the system will recognize that, and that's handled through an extended attribute attached to the various files, which is the format method attribute, and it's handled by the same sandbox that is handling the system integrity protection. And you cannot add or delete this extended attribute of the file. It's completely managed by the system. So what happens? So let's say the documents folder is protected by default by TCC. So let's say I have a password txt. I want to print it out, and I got an operational operator because terminal wasn't granted access to the documents folder. But if you take your password txt from Finder and drag and drop it into terminal, you show an intention that you want to give terminal access to that specific file. And at that moment, terminal is granted access and you can print it out. And what happens in the background is this Apple method attribute is being attached to the file. This is built out of a header, which is usually started 0300, and then there is a UUID. So down here you can see kind of more human readable, if UUID is human readable at all. But basically, this is a unique UUID which refers to the user and the application itself. Every application on macOS has a unique another UUID, but this is a different one. So this is like a locally significant UUID. And so this is how this permission is being tracked, the intention.
Yeah, so now when you know how the TCC works, let's start to talk about the first category of vulnerabilities, that is TCC bypasses through plugins. So the main problem with TCC is that the code signing requirement that you saw in the database is only about the main executor. So if you have a plugin that will be somehow able to execute code inside of the main executable context, the TCC will, say it's okay because the code signing requirement is met, because it's still the very same static file with the very same main executable. So the plugin in the end will inherit the TCC permissions. But let's see on this following slide how it will work. So we have a system application with plugin. We have kernel and the TCC user space daemon because it works on user space. So when the system application says, okay, I want to access files from desktop, the request goes to the kernel, right? The kernel will give the permission. But the kernel doesn't know if this application should be able to access the desktop or not. So it will delegate this decision to TCC daemon. So it will ask the TCC daemon in user space, hey TCC, please check if this application should be able to access desktop. And the TCC daemon will then perform the code signing assessment of the requesting application. And if everything else okay, if the validation is passed, it will give the message to the kernel that the access is granted, and the kernel will grant permission to the system application. But what happens if that plugin in that system application is malicious? We have still the very same system application, but now with malicious plugin. It's the same situation. The TCC won't know that the application has a malicious plugin loaded. From its perspective, the code signing requirement is still the same. So that's how the first vulnerability was born. The TCC bypass via changing NFS home directory. It's a vulnerability that's still being assessed against network security bounty for over 1 year. So yeah, the directory utility has a private TCC permission that gives it an ability to modify sysadmin files. And in the same time, the directory utility has a plugin subdirectory with DA plugin extensions, and these are bundles with dynamic library that is loaded to the main process of the directory utility. If you open the Task Explorer, it's a process inspector tool, you will see that these plugins are indeed loaded into the context of the main process, of the context of the main application. And this directory utility has the NFS home directory entry, which points to your home directory. Right? It's similar to $home on Linux. So this is how macOS knows where is your home directory. But you remember when we talked about the architecture of TCC, I thought that each user has its own TCC database, right? So TCC has to somehow know what database it should load. What's the path of your local users to the TCC database, the S2 database. So I decided to reverse the TCC server, and it turned out that in the end it gets the information about your home directory from get function by UID, C function. And that function gets the information from Open Directory daemon. And as you can see, the home directory is indeed here. So, yeah. Now connect the dots. We have the directory utility where we can modify data in the Open Directory, and the TCC daemon that loads the database based on an entry from that storage. So when we simply load the plugin change the NFS home directory variable, the entry, we will force the TCC daemon to load this database from a directory that we control. So we can just place a fake TCC database and force the TCC daemon to load the fake database with our fake entitlements. So this is the demo how it works. So let's take a look, for example, on the address, the contents, operational purpose. So terminal doesn't have access to the address. Let's try to change the NFS home directory. It requires root, so that's why it failed. So let's use it with root. And the NFS home directory is not changed to the EMP's bypass. Now let's restart the TCCD, so the daemon, so it will load our fake database now. We'll just stop it. Now we start the TCC daemon again. Let's kill it. Make sure everything was restarted. And now when we try to access the address directory, you will see that the permission has been run. We've loaded a fake TCC database with fake permissions. Okay. An example of bypass plugins was via Core Audio daemon. As you can see, two interesting entitlements: the private TCC manager entitlement, and the disable library validation entitlement that will allow us to load into the Core Audio daemon not Apple signed dynamic library. And why the Core Audio daemon has this disable library validation entitlement? It turns out that you as a developer, you may extend the Core Audio daemon and, for example, load your own driver for music reasons, for example. So the idea of the bypass was really simple. We just created a new driver, a malicious driver. We planted it into the HAL drivers directory. We started Core Audio daemon, and we again execute code inside of the Core Audio daemon context. So TCC, yeah, okay, it has the permissions. And because of the private TCC manager entitlement, we can now control the contents of the SQL-free database. So what I've done was just abusing the Apple's private function that they use in the private framework, and I added the terminal, the full disk access entitlement. System was all files, the full disk access, so I can do with the disk whatever I want. And here we have the demo again. So as you see, this access, it's empty. No executable here. And again, let's try to list the address book. Not permitted, but sudo also, because even if we are not able to bypass the TCC. Now let's turn on the exploit. As you can see, the terminal was added to the permitted executables. I restarted the terminal because it has to be loaded once again. And now when you try to list the address book once again, you will see that the permission has been run. So yeah, we've managed to bypass TCC one more time. Yeah, so another idea, another category of TCC bypasses was to inject to a kernel process. But we have the system integrity protection in place. You remember when I said that it's not possible to inject to the system processes. The system integrity protection will disallow that. But there is one exception. If there is that entitlement set on that executable, on the system executable, get plus allow, it's probably somebody in Apple forgot to remove this entitlement after the debugging process or someone. you can actually inject even to a system process. So I found that the Axon CPL has a private TCC entitlement and has the get was allowed entitlement allowing us to debug the process. So what I've done was just injecting with the debugger to that process that proved us that we can take over the process, because if you have a if you debug the process, you can execute code in its context. So once again, the TCC private entitlement was abused. We had a partial TCC by this. And this category of vulnerabilities, the process injections, are really bad for third-party applications, because usually the third-party applications do not have the same position as system executable. So when the developer makes a mistake, will disable the library validation on, will not turn the hardened runtime on. We can, like by system feature, inject the process. And if the third-party application, for example, Zoom on macOS or any, for example, Electron app has a permission granted by you. For example, you have a WhatsApp, you granted it a microphone permission. Usually some attacker will be able to inject to for example, to WhatsApp and take over its microphone permission. So we found many vulnerabilities with Csaba via process injection. Up to this day, we are still finding them. And for example, some of these vulnerabilities were fixed, but as you can see, for example, Firefox on macOS is still vulnerable, and they say that they won't fix it. And if you are interested on how we did it, there's my blog post about it. If you still want to exploit Firefox, because it's not fixed. Now, just
So yeah, for Electron application, I recommend checking out the Electron framework page. What kind of application using Electron frameworks, and you will find there like small applications like Microsoft Teams, WhatsApp, and these. Those are all vulnerable for forever. So we are just halfway, but you might get the impression that TCC is completely broken. Well, it's even more broken. So a couple of more bugs. The APFS file system on macOS supports the concept of snapshots. Basically, you can make a snapshot of the file system, which is a point-of-time snapshot, and you can revert that snapshot. What you can do with this snapshot, you can mount the snapshot in a custom location wherever you want, and it will give you a read-only view of basically the entire file system in that given time. So basically what was the bug or a TCC bypass with snapshot, what you could do is mount the snapshots in a custom location, like maybe 10 snapshots, and basically through the pass you could access every privacy protected file, like desktop documents, address book, whatever, because the pass wasn't in the user home directory and documents. It was something like temp something, which is outside of the scope of the privacy protection. Apple fixed this, and nowadays what happens if you want to mount a snapshot, you require full disk access. Why is it a problem? Because as we saw, full disk access is a system-wide permission, and it's granted for applications. So in case you have a macOS system, which is multi-user system, and you, let's say, grant terminal full disk access, what the other user can do, the other user can use terminal to mount a snapshot, and with setting the no owners flag on the snapshot, the file system will be mounted with no owners, so that means he will get read access to every single file, even other users' file on the system. And actually Apple said that, yeah, that's fine. So the next vulnerability. So we talked a lot of times that one of the TCC databases is a SQLite database stored in the user home folder. And this database file is protected, so you cannot, I think you can't even open it for reading, so, but you definitely cannot edit that file. But what you could do is create your own TCC database file, put it inside a disk image, and take that disk image and mount it over this directory where the original TCC database is stored. So once you mounted the disk image over this directory, basically your disk image or the files stored in your disk image will be the primary ones that the system will access. So you just mount over this directory, you restart TCC, and yeah, you just put in a custom TCC database in this location. And so here's a short demo of this. So we try to list documents. It's not permitted. We run our exploit, which will create a TCC database, a disk image, mount it, restart database, and after it we can access the documents. There is another category of TCC bypasses, which I look at it as a category. So there are certain applications that have access to private files, either because you granted access or either because they are Regula binaries and they are explicitly granted to some private entitlements. And some applications do move around files when they perform various operations, and sometimes this combination happens. So let's say you have a malicious application and you have another application which can access private files, and at the same time it can also move files to another location. So let's say you discover that hey, there is an application that can do this, and what you can do is somehow interact with that application and tell it that, hey, can you take these private files and copy it somewhere else. That application will be happy to do it, and yeah, you are done basically. So the very first vulnerability was impacted the Notes application. Notes application has access to the address book, to your calendar, and to your reminders. These are all private entitlements that only actor binaries can call. And the other thing we need to know is the nodes. So when you create a node in the Notes application, those nodes are not protected by privacy, so they are not part of the privacy protection. And when you attach a file to a node, basically it will store that file in its nodes directory. So what you can do is just say that I want to open the address book file, which is a static renamed file, with the Notes application. So what will happen, Notes will open that file and copy it inside a new node. And the new node is not under privacy protection, and at that point you can access those files. The next one is using the app translocation feature. The app translocation is a security feature which was introduced a couple of years ago by Apple to actually mitigate another vulnerability reported by Wojciech Reguła. So let's say you download an application from the internet, not from the App Store, and you don't copy it over to the regular application directory where usually applications are stored, but you directly run it from the download folder. To mitigate some vulnerabilities, what Apple does, it will not copy, it will kind of map that application directory to another location. So that's a null fs mount, which is on Linux system, it's generally available. On macOS, you cannot make a null fs mount, only the app translocation binary can do that. But basically, you make a mount of that application in a different location and run it from there. So, and it's in the temporary directory app translocation BD and the application name. This app translocation is open source. It's in the security library, and it's the LSD binary. So this LSD binary, which handles the translocation, has the system policy all files permission, which is the full disk access. So what we can do, we add the quarantine attribute to a folder which we want to translocate. So in this case, the library directory contains all the address book, basically everything except the documents and desktop and then some other files. But like 90% of your other files. And you call the translocation service that, hey, I want to translocate library. And it will do that, and it will translocate it for you. And again, since this is a different location from the user home folder, it's not part of the privacy framework protection, or at least it wasn't. And you could access every file. And since the app translocation feature is open source, it was really easy to write an exploit for. So here's a demo of that. So we try to list messages, which is your iMessages. Of course, it's protected by PCC. We call the translocate feature on library. It will be translocated to this new location. And through the new location, we can access the files. Another interesting finding is that Apple told that the desktop, the documents. So all this private information is only stored on specific location. I read a blog post about from someone. It was a forensic blog post, and someone found that the database somewhere in the system contained some private information. And I was thinking, okay, are there any other locations? And what I did, I simply run a grep. I revoked every privacy permissions from terminal, and I simply run a couple of greps on my home folder for some emails or phone numbers, some messages I had, to see if any of those private information can be found anywhere else than the actual location they are intended to be. And turned out that yes, it's all over. And these are really leaks. So it's like not full bypasses or anything like that, but you could get plenty of information like file names, contacts, family member names, the knowledge C, which is I think the core to the database. That was the most powerful one. It contained like full messages inside, the full contact list, everything basically. The front-end database contained full download history. So basically the Safari, your Safari history is also privacy protected. So attackers don't have the ability to see what pages you browsed, but at least they can check what you downloaded. They said they will not fix this. And there are a couple of more. And
Still being fixed.
yeah, still being fixed. So you can go and do some grabs. You may still find some there. So so we reported all of this to Apple, and just to share with you our experience with the Apple Security Bounty program, because they have it since 2019, I think. So they have a dedicated category for privacy, with some really big numbers as promised for payout, depending on how big is the problem. In fact, they do pay what is promised. But I think none of us got the 100K, so that should be like something really major. But we got over 50K. So they do pay eventually, and I say eventually because it just takes an awful lot of time. So the way it works is you report something, Apple makes a fix which can easily take over a year. I have bugs reported for Autonomous. Now we are in Big Sur, and those bugs will be only fixed in Monterey, which is the next release. So easily like 1.5 or 2 years pass. Sometimes, not always, but some bugs have a really long lifetime. Once the bug is fixed, they will do a review if you are eligible for a reward or not. Now that review can also take a year. So you can easily go from reporting to getting paid like 3 years. So it's not always the case, but it's also not an outlier. So it happens much more frequently than you would like to see. And the other issue with ASB, if it wasn't enough in the first place, the lack of communication. So there are only a handful of people handling the cases. They might be overloaded, and many times if you send emails, it just goes to the spam or to some black hole somewhere in the Apple mail server, and people just don't reply. And actually this is not unique to the ASB, that's just a general Apple thing that they don't reply to emails. So yeah, this is just takes too long. But if they pay, on the fair side, they don't want to hide, so they eventually do pay. But again, it can take incredible time. So as a conclusion, I think the idea of privacy or protecting certain resources with DCC is a really nice effort that doesn't really exist on other platforms, but maybe Android, but like Windows and Linux. So we think it's a step in the right direction, and others should do that as well. But it has a lot of issues. So one big issue is all the third-party application, especially the Electron on the top. That's a big problem in itself, and Apple binaries have way too many exceptions. So Apple itself granting its own application pre-granted permissions, as we saw, and the user doesn't have to acknowledge, like the Notes application. You don't have to grant Notes access to your contacts because it has access to your contacts. And there are way too many exceptions, and there are way too many opportunities to abuse these exceptions. And ASB, their boundary program has to improve. Thank you very much.
Thank you. Any questions?
So you said that this is a good step or one step for the right direction, but this case I see that it is fundamentally broken and under-designed system. So it just makes false sense of security. So I don't understand why we turn it on at all.
It's a step to the right direction.
Thank you very much.
A step.
So the idea is good, but yeah, it has.
But it looks like Unix systems back in the 70s, like we still patch those all the bad ideas with all the sudo and other concepts, but it is just designed and deployed at the same time with hundreds of possibilities to work around.
Yes.
Crazy.
We cannot disagree.
Okay.
Questions? Okay, so if you don't have any questions, we will have a short break, 15 minutes, and then we'll continue.
Thank you very much.